The doctor suspects thyroid gland trouble, which can cause various changes in the work of the heart. Until recently, it was very difficult to determine whether a person's thyroid gland functions properly. Now this can be done by tracer techniques. This is a solution of radioactive iodine. The patient is asked to drink it. The radioactivity of the solution is so insignificant that it is harmless. The subsequent course of the investigation is based on the fact that most of the iodine which enters the organism collects in the thyroid gland. Therefore, a counter registering radioactivity is placed next to the gland. The radioactivity it registers is recorded. The record will show how quickly the iodine reaches the gland. In this way, it is possible to establish whether the gland functions normally, to detect all abnormalities, and begin treatment in good time. Tracers may also be used in studying plant life. With their help, it is possible to gain a deeper insight into the assimilation of nutritive substances by the leaves. For this purpose, the plants are sprayed with a fertilizer containing radioactive phosphorus as an admixture. The leaves and the roots of the plants are then placed on photographic film, utilizing the property of radioactive phosphorus to expose it. The developed film gives a clear picture of the distribution of the phosphorus fertilizer inside the plant. Beets, for example, were found to accumulate fertilizers in the roots. It was also found that in several cases, mineral substances move inside the plant not from the roots to the leaves, but from the leaves to the roots. This lent scientific support to the case for feeding fertilizer to parts of the plant other than the roots. New ways were thus discovered of increasing the yield of many crops. These are rolls of steel band. The steel seems identical. Actually, these are different grades of steel. To distinguish them, it was customary to mark them with paint or tag them. But in the course of chemical or thermal treatment, the marks or tags often disappear. This mark is still legible. But try to make out what grade of steel was used for this band, or this. In such cases, a sample had to be taken and tested in the lab. Now the steel is marked reliably with radioactive isotopes. A small amount of the isotope is simply welded to the surface of the steel. The number of such marks indicates the type of steel it is. The radioactive marks withstand all types of treatment. It is enough to pass the steel through a device registering the radiation, and depending on the number of such marks, it determines the grade of steel. There are highly interesting applications of tracers in metallurgy. Here's a cross-section of a blast furnace. The lower part of the half block, is under tremendous pressure from the molten metal and the ore. High temperature also acts upon it. The half block consists of 10 to 15 layers of refractory brick, but even this cannot stand up to the continuous action of high temperature and pressure. Layer after layer of the brick is destroyed. The half block becomes thinner. Should it be destroyed completely, the molten metal will surge out and cause great trouble. This must not be allowed to happen. Tracers are also used to control the state of the half block. The laboratory at the iron and steel mill makes ampules containing radioactive cobalt or some other isotope in a small dose which will not affect the quality of the metal. When the furnace is overhauled, the half block is laid anew. The ampules with radioisotopes are placed in the brick. Now when the furnace begins working again, the ampules will be watchmen, stationed throughout the thickness of the half block. Samples of the metal are taken from each smelt. They are subjected to a radioactivity test. The first samples do not exhibit any radioactivity. That means the half block is in order. This is recorded in the lab. The blast furnace continues to operate. Again, samples are taken. And again they are tested. This time the instruments detect a certain radioactivity of the metal. We now know that the first ampule has melted and the radioisotope is mixed with the metal. That means the top layers of the half block have been destroyed. In this way, tracers can be used to follow the destruction of half blocks in blast furnaces. Here is another example of the use of tracers in metallurgy. When poured into the casting mold, the metal is covered with lamp black to warm the ingot, as iron and steel workers say. If a lot of the black gets into the ingot, this affects the quality of the metal, and when it is rolled, there may be much spoilage. Tracer techniques furnish a key to learning how the black is distributed in the metal. First, the black is simply mixed with a small amount of radioactive phosphorus or carbon. Then the black is placed in the mold. After the rolling process, samples of the rail are taken for testing. When the samples cool, they are placed on sensitive film. The radiation darkens the film, and we can see how the black is distributed in the metal. Here are samples of the metal rolled from the top part of the ingot. You see they contain much black. In the next samples, there is less black. These samples come from the middle of the ingot. Here there is no black at all. Tracer techniques thus afford a possibility of considerably improving and simplifying quality control in metal production. To obtain certain kinds of steel, ferrochrome is added to the metal. It is believed that about 40 minutes were needed for the ferrochrome to dissolve and mix with the metal. The smelting was planned accordingly. How much time the actual melting of the ferrochrome took and how much time the mixing, nobody knew. Tracers made it possible to establish this. Ampules with small amounts of radioactive chromium were prepared in the lab. The ampules were placed in the blocks of ferrochrome. Then the blocks with the ampules were added to the ferrochrome, which was to go into the open half furnace. The time was noted. At intervals of time, samples of the metal were taken for radioactivity tests. What did the tests show? It was found that the ferrochrome had dissolved in the metal 10 minutes after the charging. But for the ferrochrome to mix with the metal, even 40 minutes are not enough. So it was that steel smelters got the idea not to wait for this mixing to take place, but to let the metal out as soon as the ferrochrome dissolves. The idea was that the mixing would take place as the metal is poured out of the furnace. This supposition was fully confirmed. The sample test proved that the ferrochrome does have time to mix thoroughly with the steel while it is being poured. The duration of the smelting was reduced by scores of minutes. During this time, much additional metal can be smelted. Soviet scientists have had to probe quite a few of nature's secrets in their effort to make atoms work for peace. The techniques placed at their disposal greatly facilitated the success of their work. Various types of atomic reactors are used extensively in the Soviet Union for research work. This is a heavy water reactor. The slowing down of the neutrons and cooling of the uranium rods is achieved here with the help of heavy water. Different kinds of instruments are placed in the way of the neutrons issuing from the reactor. This instrument serves to study the process of neutron disintegration. Here, scientists study the collisions of low-energy neutrons with the nuclei of heavy hydrogen. This sheds light on the nature of nuclear forces. Big and highly complicated installations are needed to study these tiny particles of matter. This is an electrostatic generator. Tremendous velocities and hence colossal energies are imparted to the tiny particles of matter in such installations. With such particles, scientists then bombard atomic nuclei to learn their structure and the nature of nuclear forces. The installations for accelerating particles are called accelerators. The electrostatic generator is one of the simplest accelerators. This is a linear accelerator. In it, the particles move in a straight line. The accelerator you see can produce protons with an energy of up to 20 million electron volts. But for many types of research, it is necessary to obtain even greater energies. Here is another type of accelerator, the cyclotron. With the help of this accelerator, it is possible to obtain particles with an energy of 25 to 30 million electron volts. This type of accelerator played an enormous role in advancing our knowledge of the atomic nucleus. Here, the accelerated particles move along in a circular route. To produce this movement, the chamber in which the particles are accelerated is situated between the poles of an electromagnet. How does the acceleration of particles take place? These are two accelerating electrodes. They are shaped like the two halves of an empty box, cut in two. Here is a drawing of the acceleration chamber. This is where the accelerating electrodes are situated. The signs of the electrodes are always opposite and change with a high frequency. In between the electrodes is an iron source, whence the charged particles come. The trajectory of every particle is curved by the effect of the magnetic field. As the particle passes from one electrode to the other, it gains speed. It is attracted, as it were, to the opposite charge. The particle moves along in a spiral. Its energy gradually increases. At the end of its route, the particle is ejected from the chamber by a special device. The electrodes are being inserted into the chamber. The air will now be evacuated, so that it should not hamper the movement of the particles. In the neighboring room, targets are mounted. These are made of the substance which is to be bombarded by the accelerated particles issuing from the chamber of the cyclotron. While the cyclotron is in operation, no one must be in the hall, for the high-energy particles are dangerous to human beings. The cyclotron is switched on. When it is operating, many particles are accelerated at once in the chamber. Several million portions are ejected every second. They are ejected into a special chamber where there is likewise a vacuum. The particles fly through this chamber and bombard the target. That is how a cyclotron works. At the Institute of Nuclear Problems under the USSR Academy of Sciences, a still more powerful accelerator, a synchrotron, has now been operating for several years. Here is the main hall where this gigantic machine is stationed, a machine which makes it possible to obtain protons with an energy of 680 million electron volts. The diameter of the poles of the electromagnet is 6 meters, and the magnet weighs about 7,000 tons. In between the poles is the acceleration chamber. In this chamber, during a fraction of a second, the particles cover a distance equal to that from Moscow to Leningrad. Their velocities come close to the velocity of light. A powerful high-frequency generator is mounted here. The frequency of the generator alters in the process of particle acceleration. This is essential because at very high energies of the particles, their acceleration is accompanied by an increase in their mass. In order that the frequency should change in strict accordance with the increase of the mass, the synchrotron has a special device called a frequency variator. Protons are accelerated in the chamber, but if a target of beryllium is placed in the chamber and bombarded with protons, we can obtain neutrons with an energy running into hundreds of millions of electron volts. By changing targets, it is possible to obtain other particles as well. The rod with the target is now being introduced into the chamber. The high-energy particles emerge from the chamber through a slit covered with thin aluminium sheet. They enter holes in the thick protective concrete wall. Through these holes, the beams of particles enter other rooms where there are instruments and devices for various investigations. To make fuller use of the high-energy particles, several instruments are placed in the path of each beam. This device is being made ready to measure proton energies. Here, a device is being adjusted to register nuclear particles. It registers scintillations lasting 100 millionth of a second. Such scintillations result from the passage of the particles through various substances. There are dozens of these devices in the room. This apparatus is for studying the forces operating between neutrons, as well as between neutrons and protons. This ring of paraffin wax serves to scatter neutrons. This is a chamber for observing and photographing charged particles. The chamber is filled with a superheated liquid. When a charged particle passes through it, it leaves a track of gas bubbles in the liquid. Here is a photograph of such tracks. It clearly shows the path of the particles in the liquid. The particles emerging from this slit are of particular interest to science. These are pi mesons. Before, they were observed only in cosmic rays, reaching the Earth from outer space. Now they're obtained in the synchrotron artificially. The energy of the pi mesons runs into hundreds of millions of electron volts. They are the glue that holds the particles of the nucleus together. This is a device for registering pi mesons. The properties of charged pi mesons are also studied with the aid of the Wilson cloud chamber. In this chamber, the particles leave distinct tracks. A magnet deflects the tracks. This is a multi-channel gamma spectrometer. It is used to study neutral pi mesons, which disintegrate almost instantaneously. By studying the products of their disintegration, it is possible to learn a lot about the nature of these interesting particles. The synchrotron is operating. All its units are functioning. The main switchboard is in another building. It is from here that all the units of the synchrotron are controlled. A sound or light signal draws the attention of the engineer on duty to any sign of trouble. Beams of particles reach the instruments from the chamber of the synchrotron through special holes in the wall. Numerous experimental devices keep a constant record of the signals reporting various nuclear processes. But where are the people? They are next door, behind the reliable protection of concrete walls. It is from here that they operate the instruments and follow their work. This gigantic machine has enabled Soviet scientists to carry out a number of most important investigations. But Soviet science is not marking time. In this building, an even more powerful accelerator is nearing completion, a proton synchrotron. Here, scientists will obtain protons with energies running into 10,000 million electron volts. This is part of the installation's magnet, shaped like a ring, with a 60-meter diameter. It weighs 36,000 tons. Inside the chamber, protons will make 4.5 million revolutions in a single acceleration cycle, covering a distance 2.5 times greater than that from the Earth to the Moon. Every part of this installation is most impressive. This will be the most powerful accelerator in the world. The acceleration of the protons will begin in the 4-injector. From here, they will pass into an auxiliary linear accelerator. The protons entering the chamber of the proton synchrotron will already have an energy of 9 million electron volts. To feed the current needed by the units of the proton synchrotron, many thousands of miles of electric cables have been laid in an underground tunnel. A special building houses powerful motor generators which are to feed the coils of the magnet. This new powerful machine will help scientists to gain a deeper insight into the atomic nucleus. The Soviet Union makes no secret of its achievements in the peaceful applications of atomic energy. These achievements were displayed at an exhibition in Geneva, which was viewed by scientists from all countries. Now it is being viewed by the Soviet people's great friend, the people of India. Scores of thousands of people see in this exhibition convincing proof of the Soviet Union's noble objectives, the peaceful prosperity of all peoples, regardless of their social systems. Many of the exhibits are now familiar to us. Here's a model of a research reactor. This is a medical apparatus for radioactive treatment. The model of the first atomic power plant always attracts particular interest. How little fuel it consumes compared with coal-burning stations. A 100,000 kilowatt coal power station requires 10,000 railway carloads of fuel a year. How much will an equally powerful atomic station need? Only 1 carload. That is why atomic power plants can be built in the most remote and desert areas which have no fuel of their own. Under its new 5-year plan, the Soviet Union is to build several new atomic power plants with a total generating capacity of 2 to 2.5 million kilowatts. Here is a model of one of the stations to be commissioned within the next few years. This mighty, atomic-powered icebreaker will blaze a trail to the heart of the Arctic within the current 5-year plan.